he's going against us.
All right, here we go. So we're going to outline the use of polymerase chain reaction. What I did in this unit was, since this is kind of my topic for now, is I just modified it to the exact things you need to know. I did not give you anything extra. There's nothing extra that I'm going to tell you. My stories will be my story from what I did, but it's not going to be anything that you need to know. We've learned in the past couple times that it's stuff that you may not need to know, but people thought it was important to know. All right, so what do you think about polymerase? What do you think about that word? What do you think that word means? Let's try one at a time. It is a, I'm hearing it, I heard it. It's an enzyme, which of course we all know is a catalyst.
So I was half right.
Yes. All right, it's a catalyst. All right, and we're going to have a chain reaction. Does anybody know what a chain reaction is? Another thing happens, similar to atom bomb. All right, an atom bomb provides a chain reaction of uranium atoms splitting, and that's why you get the explosion. All right.
Is it like dominoes?
Yeah, like dominoes, chain reaction. All right. So PCR, polymerase chain reaction, is a way of producing a large quantities of a specific target of sequence of DNA. What is a sequence of DNA called? What a specific target? What is it called when we just look at a certain segment of DNA? I heard it. All right. Segment of DNA equals a gene. So we're looking for a gene. All right. A segment of DNA is a gene. It is useful when only a small amount of DNA is available for testing. So if you go into the crime scene, the forensics, all this stuff is forensics. This is what it is. Crime scene blood samples, semen, tissue, and hair. Those aren't the semen that are in our Navy, by the way. That's not what we're talking about here. Okay. PCR occurs in a thermocycler and involves a repeat procedure of 3 steps. This is a thermocycler. All right, this is it right here. All right, we own these thermocyclers, okay? So in this one, I can do 25 samples at once. I can do 25 different genes at once. All right? It's a lot. But considering that there's 3 billion base pairs, 25 genes is not a lot. But remember, the human genome only has between 25 and 30,000 relevant genes. The rest that we have, 70 to 80,000, are just junk. They're horse flock, they're corn. They could be some dog DNA in your DNA. There could be some oyster DNA. It's junk DNA. It doesn't do anything. Okay? It's called STRs. All right.
I have a question.
Yes.
Why do you have those? Do you like use them?
Only on the weekends. I come up here.
No, seriously.
Yeah, I take students' hair samples and then I sequence them out and then give them a drug to make sure. No. You use them.
You just use them for show.
You use them.
Wait, that's
We'll talk about that. We'll talk about that. All right. Not today. You don't even know what to do. How can I give you that piece of equipment that's $4,000 and let you use it if you don't know what to do? All right. All right. Denaturation. Denaturation. What is it to denature? What are we doing? Break it down. So at this point, you're denaturing to separate the DNA strand. So this is through heat, right? A change in the heat. All right, you'll denature something. You'll break it down. It'll change its form. Then you need to anneal it. Annealing is when the gene that you're looking for, you add a primer on each end. So once you add a primer, and I'll have a picture of it on the next slide. Once you have a primer, it's going to attach to the opposite ends of the specific gene you're looking for. Now you do this thousands of times. All right, my old job, somebody asked me, well, how many times did you do this? About 150,000. Well, how many genes did you find that were actually worth something that somebody else didn't discover? 9. 9. 9. When you find one You go running around the building with employees, about 100, 150 people, you're screaming at the top of your lungs, and they usually have champagne at the end of the day. Because that gene then, we would patent. And we have a patent on it today that if a drug is developed from that gene, we get paid. All right, we get paid. But judicial law is the Supreme Court saying we might not be able to hold a patent on the human genome part of that gene. So it's getting debated right now. And I did this stuff 15 years ago. Okay? Yes.
Does that mean even though you're not working, you get money?
Yes. Yes. The same people that developed penicillin, our old AD, I think I told you this. His dad was one of the 9 people that discovered penicillin. Yeah. They're still getting jack. All right, still getting it. All right, even though we don't use penicillin as much, but they're still right. I am too. All right, elongation, a heat-tolerant DNA polymerase, Taq polymerase is something you need to know. We used to use this all the time. Taq polymerase is what it's called. You can say TAQ, but if you're in the biz, it's Taq polymerase. All right, copies of the strands. Because why do I say that? Because when I went over this with the teachers on Wednesday, they're like, TAQ. I said that's Taq polymerase, not TAQ. It's Taq. All right. You know, whatever. I mean, come on. All right.
Are you teaching like the teachers this stuff?
Yeah.
I feel like you are.
Taq. It's just the sequence part. Yeah. All right. One cycle of PCR yields 2 identical copies of DNA sequence. And now check this out. This is what I love. A standard reaction of 30 cycles would yield 1,073,741,826. That takes 1 hour in this machine. 1 hour in this machine to make 1 billion copies of a gene of DNA. Okay? Not bad. Not bad, right? All right, so now what we do is this. We take out our, take a look. So this is just a little picture of what it is. So we have the copy. All right, so this is the extracted DNA. All right, so this is my extracted DNA. Here it is. So the first thing I need to do is heat to separate the DNA, and that's called all right. And then from there, so what happens? That's going to separate the DNA. We all know that we have 2 strands of DNA. It has to separate it out. What are these guys that I added right here? Who can remember what these are? Those are primers. This purple part right here. That purple is a primer. This is going to be primer 2. This right here is going to be primer 1. All right, primer 1 is going to attach on the front end. Primer 2 is going to attach on the back end. Boom. Because why? These are the corresponding complementary base pairs. At GC, right? At GC. At GC, right? At GC. All right, and then we're going to extend that nucleotide chain. So what we're going to do, add some primers, we're going to add some nucleotides. Now we could just take some ATs, Cs, and Gs and throw them in there. We can make them in a liquid, and we can just throw them in there. It's just a chemical. It's no different. All you are is made up of chemicals. That's all you are. Chemicals and electricity, of course, go hand in hand. You could plug into a power outlet and survive. It's a later on lesson. We're going into the human body next. All right, now, here we go. What is this right here? And this guy right here. It's not the primers anymore. Now we have a full copy of our new genes. Full copy of the gene. Okay? So this is the new gene. This whole thing right here will be a gene. This is copy 1. This is copy 2. All right? So full copy of the gene. And all we did was, at this point, extend the nucleotide chain using DNA polymerase. All right, so we're going to use DNA polymerase. All right, so we're going to break down exactly how to do PCR. Because in maybe past units, that's all you get. But we're going to look at it in a simulation. So what you need to do is pull out your topic 4.4 activities. This sheet right here. Okay? This sheet right here, topic 4.4 activity sheets. Don't worry about it. Just go with the flow. Oh, just go with the flow. Yeah. Yes. I am still recording. I didn't stop recording.
Shout out.
All right. PCR. Short for. You are in IB biology. Why are you surprised by that?
Polymerase chain reaction.
All right. I wrote IB biology activities on the top. All right. I made this the other day. That's what I did. All right. So what you're in, okay, I could have said Homer's PhD IB biology, but we're just using IB curriculum. What's the big deal? All right. Is a relatively simple and inexpensive tool that can focus a segment of DNA. What's a segment of DNA? Gene. So I think I should be answering number 3.
What?
What?
What are you ugly?
PCR can be used every day to diagnose diseases, identify bacteria and viruses, match criminals to crime scenes, and many other ways. All right, so you should be through number 3. Segments of DNA, which are genes. 3 billion base pairs.
Is it 3 billion exactly?
Right around 3 billion.
What do these two uses of
Oh
PCR?
god, my stomach.
What are 2 ways that we use PCR? Diagnose diseases, identify bacteria or viruses, match criminals to crime scenes, many different ways. So those are the 3. Those are the 3 big things that we use PCR for. Okay? All right, it'll get a little easier after that. All right.
How many base pairs do you have? 3 billion.
All right. So there you go. You were asking me this question. The human genome is made up of 3 billion chemical base pairs. Scientists often need to isolate a very specific segment of DNA within a vast amount of genetic material. Since this segment is one tiny piece of the genome, you need to make many copies to have enough to work with. Okay? So that should be number 3 or 4. You should be up to number 3 now. We haven't done number 4 yet. No, we haven't done 4 yet.
They isolate a segment of DNA.
All right, I'm not going to tell you. Just follow along. Go. I mean, really? All right. So, what do you have for number 4?
Nucleus.
The nucleus. Oh my gosh.
Can we replay that little bit?
All right. The polymerase chain reaction, or PCR, can generate 100 billion copies of identical copies of DNA sequence in a matter of hours. As the inventor of PCR explained, the technique requires no more than a test tube, a few simple reagents, and a source of heat. There you go. So that is number 5, I think.
Simple. So
heat.
hard for heat.
Test tube.
I got a source of heat.
Heat test tube. Huh?
It's probably right on the board. Reagents are the primers, the nucleotides, the DNA polymerase. Reagent is any chemical. Okay. Now you're getting it. All right?
Yeah. Hair.
To perform PCR, a PCR reaction, you need DNA that has been extracted from cells. Because the purpose of PCR is to make DNA copies, you don't need very much DNA to start the reaction. For example, you could extract DNA from a small sample of blood, skin, saliva, or even hair follicles. Follicles is one hair.
Wait, even just like that? I
It's a
thought
follicle.
it had to be. It had like a root on it.
Yeah, I know.
follicle's not like that. Now here's a question for you. Anybody ever remember Blockbuster?
Yes.
Does anybody know anybody that worked at a Blockbuster? Do you know what they had to do in order to work at the Blockbuster? They have to provide a sample of hair. Why?
So nobody steals their movie.
What?
Not because about lice, and not because of stealing. Because what they would do with that hair is if you had marijuana, it would show up in your hair anytime that you had marijuana. So from 30 days after your hair is grown, so if you shaved your head and your follicle was tiny, say you wouldn't be able to do it. If you have long hair, every single drug Simone or Tess or Kathy has ever done is in their hair right now.
No way.
Way.
Better cut out the-
So cocaine is 6 months. Heroin is 9 months. So they could tell every single drug you've done from any different part, 30 days. So if you had marijuana January 15th and you hadn't cut your hair, it's in your hair. All right? It doesn't go away. It just shows where it is. Yeah. Just so you know.
So what, after 30 days, just stops?
That is so funny.
All right. All right, so here we go. PCR. Start moving your extracted DNA into a special PCR tube. PCR works by heating and cooling the solution over and over, so PCR, God bless you, are designed even as a heat distribution. All right,
Heat design.
what's the question?
What are you using to move?
Oh, I haven't done that yet. All right, ready? So this is what we have. We have some ice buckets. We got our chemicals, our reagents right here. We have our tube, we have our thermocycler. These are micropipette tips, and we're going to be using a micropipette to move it. All right, check it out. Here's my micropipette. See it? There it is. Micropipette is what I'm going to move. I will be moving that. Micropipette. Micropipette. So I'm going to go ahead and do this. Now, when you're using your micropipettes next week, all right? You're going to use micropipettes next week. All right. You push it down. So on this, I got to hold it. There's something bothering you on your iPad. Let's put it away then, because it seems to be distracting. Okay. All right. You hold down the button till you get to the point, and then you have to bring it over and you let go, and then it comes out. So I actually have to do that with my cursor. So I have to hold it down and suck the stuff out. So I'm going to suck this stuff out. All right, and I'm going to move it over here to my tube. All right. All right. So, and then I discarded my micropipette tip because you can only use one tip at one time. All right. So what did I do? Number one, once the extracted DNA is in the PCR tube, which is on ice, what must you add? Primer 1 to the PCR tube. Primer is attached to sites on DNA strands that are either end of the segment you want to copy. Primer 1's on the leading end, and primer 2's on the lagging end, which you don't really need to get into. They are powerful tools for copying very specific DNA sequences. There are almost no chance they will target the wrong site. So actually 8 and 9 are both what? Primers. Okay. 8 and 9 are both primers. Primer 1 is fine. No, both primers. 9 is primers. 8 is primer 1. All right, so here we go. I'm going to drag primer 1. All right, I'm pulling it. Look at that. All right, so I'm going to bring it over here. I'm going to put it in there.
What if you don't do it right?
It won't work. Now add primer 2. All right, so I'm going to add primer 2. Yes.
What happens if you put primer 1 in before you put primer 1?
I don't know, Jake. What did I just tell you? Won't work. All right. Now we have to add our nucleotides, which are just simple chemicals: A, C, G's, and T's.
Oh, see, I need to attach after primer 1.
Where will primer 1 attach? What did I say? The beginning of the sequence.
Hold on. This is after primer 1 is added. What is next? Nucleotides.
It's primer 2, second site, then nucleotides, then AC.
Second site. Number 11, in order for PCR to work, you must add nucleotides A and C, G's and T's. All right?
So which one of those comes from us?
The original DNA. All right? So I'm going to add these nucleotides over here. I almost missed it there. Last, you'll add DNA polymerase to the PCR tube. DNA polymerase, tiny molecules act like tiny machines that can read DNA code and attach matching nucleotides to copy DNA copies. This particular DNA polymerase has been selected to withstand the high heat of PCR reaction. All right, let me do that. All right, so when you do this, is it going to be hard? No, you've seen it. You're just adding these pieces in there, and then we get to that point. Now that the PCR tube is filled with reaction components, we're going to place it in a DNA thermal cycler. DNA thermal cycler.
That's 13. Wait, DNA.
This machine can precisely heat and cool your tube at specific times during the next hour. These changes in temperature are crucial for making the reaction work. All right, so that's not good.